all for coming today to this meeting of the Journal Club. Of course, Dr. Ilyas usually chairs it, but he had a meeting, so I am also the member of the physics department filling in his place. It is, excuse me. We're very fortunate to have with us Professor Ali Bumajdad from the chemistry department here at Kuwait University. Professor Ali got his PhD from Bristol University in the UK and is a member of many chemical societies, including the Royal Society of Chemists and the Kuwait Chemical Society, among others. He is very active in research and is an expert in nanotechnology. So he will tell us. We're very fortunate to have him speak to us about nanotechnology. Thank you, Professor Ali.
Thank you very much for the nice introduction. Assalamu alaikum jami'an. I'm very glad to be in the physics department. This is my first time to give a talk to the physics department. But I came to this meeting room several times. They always invite me when you have a gathering, and Dr. Amina and Dr. Yassar and all other colleagues, Dr. Mustafa Marafi. Actually, some of them were my teachers in my bachelor degree. I studied with Dr. Adnan Yassin, Dr. Mustafa Marafi, and Dr. Adnan Muqaddasi, as far as I remember. Yeah. So I respect the physics discipline, actually. I think it's the father of the science. Maybe I'm a chemist, but I really think that physics is the very important field of science. And we teach our students. I'm a physical chemist, by the way, so I know a little bit about physics, not expert, but because I teach physical chemistry, I teach thermodynamics, kinetics, this kind of thing, so it's related to physics. When we teach our students, we always talk about the physicist, and we always tell them, for example, when we talk about theory, atomic theory, Dalton atomic theory, we tell them Dalton is a physicist. When we talk about the Rutherford experiment, for example, to discover the nucleus, we tell them he's another physicist, and Einstein, and so actually at that time the physicists were actually leading the science, and that we are getting the benefit of it now. Of course, we have also Stephen Hawking and the recent photography of the black hole. Also, this is physicists behind it. So we really. I admire this discipline, and I think people who decide to study physics actually are ordinary. Not ordinary. They are actually, let's say, special people, special students. Even some, by the way, in my opinion, even some of the medicine students cannot cope with the physics as a discipline. It needs different, actually, let's say, skills. Okay. So I'm going to talk to you about nanotechnology. This is actually the field that I worked on for the last 20 years or so. This is actually relatively recent science, because the discovery of the term nanotechnology only used actually in the 70s of the last century. So we'll say that's around only 50 years. But there was many, let's say, evidence that the nanotechnology was used much way before that timing. But at that time, they didn't call it nanotechnology. They used to call it, for example, colloid science, because colloid science. I don't know if you are familiar with colloid science. Colloid science is talking about particles in the dimension from 1 nanometer to 10,000 nanometer. Okay, dispersed in another medium. Nanotechnology is talking about particles from 1 nanometer to 100 nanometer. So there is actually part of the colloid is actually nanotechnology, but they don't call it at that time nanotechnology. Okay. Faraday have very famous actually experiment related to the gold, and this was way maybe 200 years or 150 years ago. So at that time they were dealing with nano golds actually, and there is some of the church and all the let's say buildings. There is signs that they are using some nanoparticles in coloring different kind of products. Okay, so this is actually, let's say, the old and new science. I'm going to talk a little bit about the definition. I'm sure you are aware of will just go through it very easy, quickly, and then I will focus on some of the applications. And after that, I will talk a little bit about preparation, how to prepare nanoparticles or nanotechnology devices. And then I'll talk about how to characterize it, because to characterize nanoparticles is not very easy, because we are dealing with very, very small particles that we cannot see it in our eye. Because our eyes can see only dimension of the visible light, maybe 300 nanometer, 200 nanometer, but not smaller than that. While the definition of nanotechnology is actually, we're talking about material with dimension less than 100 nanometers, so we cannot see it. And at the end, I will talk about some of my research in the field. Okay. So this is actually the definition. The nanotechnology is talking about material or devices at the size of a billionth of a meter. So 1/billion of a meter, which is 1 nanometer. By the definition, usually we are saying from 1 to 100, but some of the material will not give you the fascinating or the, let's say, the excellent properties changes. If you talk about 100, we have to go much lower than that. For example, for gold, we don't get the interesting result unless we make the gold less than 5 nanometer. Even 6 nanometer will not give us a very interesting result. So when we say 1 to 100, this is, let's say, the frame, but for some material it has to be smaller than that, much smaller than that, to get the fascinating properties. So the scientists discovered that when you make the size of the material very, very small, that you cannot even see it, there is a major change in the properties. Very, very interesting result, actually, that will maybe make us focusing on making the particles smaller or the material smaller rather than searching for another element or new element. Because it's very hard to find a new element, but we have all the elements in the periodic table. I just try to make it smaller, and I will have properties as if it is a new element. Okay, so you can transfer, for example, the magnetic material to let's say the material with no magnetic property to a magnetic property, to excellent supermagnetic magnetism, for example. Or a material that is soft, you can make it super hard, harder than the diamond, for example, by just changing the size of the material. So the properties like surface area, it's greatly actually enhanced by decreasing the size of the material. And this is very important for field in chemistry. We call it the surface chemistry or the catalysis, which is very important for the petroleum industry. All the petroleum product need a catalyst. Most of the reaction need a catalyst to speed it up. So in order to enhance the catalytic property, we just need to decrease the size and increasing the surface area. The conductivity, some of the material actually decreases by decreasing the size of the nanoparticles. If you have conductive material, you can make it semiconductor by decreasing its size. So we have silicon, the famous semiconductors, but now I can make copper semiconductors by decreasing its size, or the iron semiconductors by decreasing its size. The melting point also decreases by decreasing the size of the particles. The specific heat also enhanced, the magnetic properties enhanced, the chemical reactivity enhanced, and I'm writing for you here a very interesting example of enhancing the chemical reactivity. We know that gold is inert, that's why it is expensive, and we call it noble metal, not noble metal, it is actually precious metal, very expensive, gold and platinum. But when you make it very, very small, you can make it active, reactive, very reactive actually. It can react even with the light, and the normal light, not UV or X-ray, just the visible light. You just expose the visible light, it will turn to be very, very hot. That will kill, for example, cancer cell, for example. I will show you carefully later on. The quantum confinement, this is very much related to physics. I didn't do a lot on this field, but I'm sure you know cadmium selenide and cadmium sulfide. When you make it into very small particles, you confine the electron to space, and this will make excellent actually properties to the physical properties, and this is called the quantum confinement, or they call it quantum dot, which would many interesting applications. The colors, for example, change by changing even 1 nanometer in size. If you prepare 6 nanometer, it will give you orange, for example. If you make it 5, it will convert to become purple. The plasma resonance, this is very important for gold nanoparticles because they use it to kill the cancer cells. They just put antibodies on this nanoparticle of gold, and then they send it to the cancer cells. And then by exposing just normal light, there will be oscillation of the electrons cloud of the gold. And by this oscillation, the temperature increase dramatically. It can reach maybe 1000 degrees. And this will immediately kill the cancer cell, for example. So there is a huge research, and people saying, we know that gold is very expensive and precious, but if you make it nano gold, it will become even more precious because of this application. Silver nanoparticles are used to kill the bacteria, for example, and they use it now to coat the bandages in the hospitals, as it will not for killing bacteria. The mechanical property is also very interesting. If you add, for example, carbon nanotubes to the cement or concrete material, you are greatly enhancing the mechanical properties, and you can make it very, very, good material. Of course, it's expensive to use carbon nanotube, but maybe for fine, let's say, applications, small applications, you need very, let's say, excellent proper mechanical properties. So you can prepare very small, maybe sample of cement with excellent mechanical properties for certain applications. So this is just in general, just decreasing the size, we are controlling many properties, but not only the size, or even the shape. The shape also affect the property. So if I have gold nanoparticle spherical, it will give me different property than gold nanoparticle with cylindrical shape. Completely different properties. Okay, so we know that for spherical particles, the surface to weight ratio, we call it, is just actually, you can get it by dividing 6 over the diameter of the particles divided by the density. And if you just do this simple math, you'll find out, for example, for 20 micrometer, this is not nano material, not nano size, 0.3 meter square per gram, so this is something like this maybe. But if you, the same particles, you make it into 5 nanometer, now we are in the nanoscale, the surface area will become 1,200 meters square for 1 gram. So 1 gram have huge surface area that will be, let's say, used in certain applications like catalysis. Surface area is very important for catalysis. Okay. Now, when the object is small, the atoms on the surface will be most of the atom will be exposed to the surface, and we have very few atoms will be hiding in the bulk. And for many applications in the solid state, you need the atoms to be exposed to the surface rather than staying in the bulk, because the bulk will not have, the material or the reaction will not have access to the bulk material. It has to react with the surface, has to be, get benefit from the surface. So I'll give you just an example quickly. This is, let's say this is 1 micrometer in size, 1000 nanometer. There is only 0.002% of the atom on the surface. The remaining is in the bulk. So more than 99.8 actually the material is hiding in the bulk, and this is only the 0.02%. Now, if you make it into 0.01 micrometer, still not in the nano size, you are exposing. We are in the nano size, 10 nanometer. We are exposing 20% of the material. 20% of the material will be on the surface, and 80% will be in the bulk. So you can see 10,000 times the amount of the atomic surface is from 20 to 0.002 is 10,000 times. You are enhancing it 10,000 times. So how about if you make it actually 3 nanometer, or if you make it 30 nanometer, 5% only. If you make it 3 nanometers, you will get 50%. Half of the material actually exposed to the surface, and half of it in the bulk. I'll go through some applications. This was actually the definition. Now I'll talk about some applications. At such small size, the nanoparticles or nanomaterial behave differently and exhibit special properties. For example, if we consider the copper nanoparticles is super hard. If you compare it with the bulk copper, you know, the copper bulk material, we can make it into wire. It's able to be, hammered by the hammer. But when you make it in the nanoparticles, it becomes very hard. You cannot make it into wire anymore. So the bending of bulk copper occur at with movement of copper atoms in a range scale actually of 50 nanometer. So if I make my copper less than 50 nanometer, this movement will be lost actually. We cannot just expand the malleability and ductility of the material will not be as good as for the bulk. So we are talking here about changing some mechanical properties by decreasing the size. Cadmium selenide, I told you, if the size is less than 10 nanometer, it will emit colorful light, which depend on the size actually, and this is what we call it the confinement or the quantum dot. This is cadmium selenide samples from 2 nanometer to 8 nanometer. You can see how the color change just by changing the size of the particles. Of course, not all the material have these properties. This is because the cadmium selenide is semiconductor, so you need semiconductors to have the quantum dot effect or quantum confinement effect. Okay, you can see this picture. This is a suspension of iron oxide nanoparticles, and this is also a suspension of nanoparticles, but not nanoparticles, iron oxide particles with larger size. You can see here it's very difficult to disperse it, while here it's completely dispersed, and it's actually colorless, transparent. So the particles are very small that even they don't scatter light. The color here because of the iron oxide is reddish or yellowish, but you can see behind it actually because of the smaller size. So actually, when you have smaller particles, you can enhance the stability of the suspension. If you have application, for example, the paint. They have to use actually titanium dioxide because the paint, the white color usually coming from the titanium dioxide. But if my titanium dioxide is not stable, it will settle down and separate, and I will lose the color. So we have to make it very stable. One of the main, let's say, the best way to make it stable is to decrease its size, because there is something called the Brownian motion. I'm sure you know about it. This is the thermal motion that happens in the solution because of the temperature, and this Brownian motion is able actually to randomly shifting the nanoparticles in all directions when it is very small. When you can make it bigger, either the density difference will shift it up, or the gravity force will pull it down and will settle down or float on top of the solution. But when you have it small, it will just stay suspended. So also the gold nanoparticles has unexpected visible properties since they are small enough to confine their electron and reduce the quantum effect. This is also the quantum effect of gold nanoparticles. No longer, by the way, no longer yellowish. The gold, when you get it small, you will change its colors. When you see it as a powder, you will see it yellow because the particles are aggregated, actually. But when you suspend it in solution, you will see different color. This is a plot showing how the gold become very reactive when the size starts to become smaller than 5 nanometer. So above 5 nanometer, the gold, there is not much, let's say, interest. It will be just normal gold. Expensive, will not react with the acid or base or any other material. So we can use it as jewelry. If it is more than 5, but less than 5, look how sharply the activity or reactivity is increasing. Very, very sharply. It become, they use it as a catalyst. The gold, which is, we call it inert, will not react with anything, even with the strong acid will not react. But when you make it small, it will be very, very reactive, and it will even react or let's say interact with the light, visible light. And this, of course, because this was very important work, it was published in Science. I don't know which year or something. 20 years ago. The gold nanoparticles, when you expose the gold nanoparticles to visible light, the electron clouds start to oscillate. So there will be partial negative and here partial positive and then opposite. And because of this oscillation, there will be development of temperature, and the heat of the nanoparticles increase suddenly, and it can reach up to 1,000 degrees. Actually, if you make it very small and you just make it sticking to cancer cell, for example, it will only destroy the cancer cell. It will not destroy the next cells because it is very small, nano size.
Excuse me, Doctor. About the density of the nanoparticle is the same as the density
No.
of the same element when it is?
No, the density will also change.
Yeah, that's why the exposed atoms are very much more in the nanoparticle.
Yeah.
And how the exposed atoms are more percent for the same element, for the other nano dimensions.
It's exposed because we are shifting the atoms from the bulk to the surface. Because you are breaking. When you break down the particles, you are exposing a new surface. So most of the particles will be on the surface. Yeah. Okay. So I would just want to show you how, for example, this is a UV absorbance for different size of nanoparticles. Maybe it's not clear here, but this is 400 and this is maybe 20 nanometer. You can see for 400 up to 100, there is not much change. But once you reach 100 and below, you can see a very clear shift in the absorbance. And that's why we see different colors for the globe. And now here, they are changing only the shape. This is spherical and this is cylindrical. Similar size, but different shape. It will give you completely different absorbance. Here, I think they are doing aggregated particles. All of them are the same size, maybe 5 nanometer, but some of them are aggregated. When you get aggregation, you get shift also in the absorbance. So it's a very interesting phenomenon. The band gap in physics, I'm sure you know that when you have, there is, for example, the titanium dioxide and zinc oxide semiconductors have very well-known band gap. This band gap is very interesting, and it's actually responsible for the semiconductor property. And this make actually some of the material can absorb the UV from the sun. You know that we have around 4% of the sun radiation is coming from UV. So if I can make the titanium dioxide smaller, I can increase the band gap. And by controlling the band gap, I can shift the absorbance of this catalyst, or photocatalyst we call it, from the UV to the visible. And this is actually very interesting because if you can make our catalyst, let's say, react with breaking down, for example, organic pollutant, just by decreasing its size, this would be very interesting. And the UV is good to use it as sunblock in our body. But for a catalyst reaction, it's better to use the visible because it's 92% maybe of the sun, or maybe, I don't know how much, maybe 80% is actually visible. So I want to use the large amount of energy rather than focusing on the 4% only. So this can be done only by controlling the size and also supporting the titanium dioxide on substrate. When you support it in another substrate, you can also control the visible, the band gap. And I did some work in this field a long time ago, and I used the titanium dioxide, and then I put on top of it gold nanoparticles. And I found out this enhanced very much the photocatalytic properties. And we found out by controlling the size of the gold nanoparticles, we get different control of the photocatalyst. And we think that because of the plasma resonance that I explained just before the gold, this will elongate the recombination between the whole electron and hole. There is a problem for the recombination of the electron to fill the hole. This will decrease the activity, the photocatalytic activity of the catalyst. So if you can keep them separated, this will make the catalytic activity better. And we did it by adding gold nanoparticles of certain size, of course, all of them less than 5 nanometer. Okay, this is the sunblock. You know that the zinc oxide and titanium dioxide will absorb the UV and, of course, prevent our body from exposing to the UV. There's many kind of applications. I don't have time to talk about it, but you name it. Electronic application, engineering application, biological, medicinal, pharmaceutical. You can see, for example, it can be used in ink cartridges, solar cells, water contamination, catalysis, as I said, sensors, and small electronic devices, unusual color paint, destructive absorbance of chemicals, biological warfare, information storage, etc. So the application is actually like amazing. This is one of the most important nano material that was discovered in this century, actually, or the end of last century. This is the buckyball. We call it the fullerene family. Very interesting ball of only carbon. This is allotropy of carbon. So we have diamond and graphene, and we have fullerenes, third allotropy of carbon. Interesting property, electrical properties. You can use it as cage. You can use it for drug deliveries and many other applications. And after that, they discovered the carbon nanotube, and they start to make single carbon nanotube, double carbon nanotube, and this one actually can become very, very stiff and hard, even better than a diamond, the carbon nanotube, if you consider the scale that it's working on. This is three-dimensionally nanomaterial. This is two-dimensional nanomaterial. It's not nano. This is not nanomaterial scale. But the height and the width is nanometer scale, while this one is actually from our side. And now there is an important discovery. All these actually they get Nobel Prize. The person who discovered the fullerene and the graphene also get Nobel Prize, because these are very important to the industry and to the applications. The graphene is actually just a thin, very single layer of carbon arranged in a hexagonal array. They discovered it very simply by just putting the tape on the carbon, and they just pull it, and then they get single layers, and then they get the Nobel Prize after that. So even this one was discovered in very, I mean, that's why we always tell the people don't, I mean, there is sometimes accident happen in the lab. The result of this accident is a Nobel Prize. I mean, so don't be afraid from making, let's say, strange things, unexpected experiment. You might get very interesting results. Such material have high tensile strength, high electrical conductivity, high ductility, high resistance to heat, and also chemically unreactive, which is good. If you want to use as drug delivery, you don't want carbon to nanotube may be also used in fabric, making fabrics for our clothes, and also can be used as the building material. I heard that now there is some contract with the petroleum Chinese company from the Japanese. They are asking them, because you have the chimney for burning oil, usually there will be some carbon on this chimney. Yeah, the soot, yeah. They buy it from them, and they think they are getting actually either graphene or carbon nanotube, and they use it as additives for their materials. So the Japanese are buying this from the big factories in China. This is just a quick look of the applications of nanotechnology. And the text side, we can use it. We can convert the hydrophilic to hydrophobic, water loving to water hating fabrics, the biomedical, the healthcare, the food industries, etc. And in my opinion, the new era of nanotechnology will be related to the healthcare and medicine. The technology actually, let's say, get the most benefit so far, but now there is slowing down in the technology part. I mean, we cannot just make the equipment smaller and smaller and increasing the space for information. We reach almost to the threshold of the development, but the healthcare now actually, and the bio-nanotechnology, let's say, is very, very prominent. This field is multidisciplinary, so you cannot just work by yourself. In my case, I collaborated with many people actually, because I need the engineer, I need the physicist. I work with Dr. Ali Rakshani several times, and Dr. Yahya. We did some work together. So we need collaboration. I did some work with engineering, with the biologist, and also abroad in different disciplines. I work with civil engineering, because I will show you now, I was trying to enhance the mechanical properties of some cement recipe. So I need civil engineer to help me, because I'm not familiar with cement. I'm familiar with the nanotechnology, that I want to add it as additive to the cement. So we did a lot of work. So you cannot just work by yourself. Physicists, material part can work with the life science and can work with the engineering. So there's big engineering circle, big material physics and chemistry, and big life sciences. All these people can work together because there is very, let's say, common area in between. How to prepare the nanoparticles? There is a physical way and there is a chemical way. Each one have advantages and disadvantages. The physical method actually is, we call it ball milling. This is the most common way to do it, but there is many other also method in physics. Lithography, for example, just using laser to make thin grooves in the samples. This is you will convert it to nanotechnology, to nanomaterial. So in this device, you just use very, let's say, stable material of maybe from marble or from metal that will not react with my material. And then this material will, this device will just break down the particles for hours and hours until it's become in the nano size. The main disadvantage, you get poly-displaced particles. The size is not the same. The different shapes you get. And sometimes there is a chance you change also the crystal, because this will generate huge heat during the preparation. So you might change the crystal structure of the material. But it can give you large amount. Usually in the chemistry you get 2 grams, 5 grams, 6 grams. Here you can get maybe half kilo or 200 grams. So there is advantage and disadvantage. The chemical approach is actually, we call it bottom up. The previous one called top down. This is called bottom up because we start from the atomic scale. So this is top down. I start with large, using the ball mill to make it small. For the chemistry, I use with the atomic scale, less than 1 nanometer, in the size of 1 angstrom. And then I make it react to get to the size of the nanometer. It's very simple, actually. You can either find a precipitating agent, you add it to your precursor, and it will precipitate as a small size. Or you can use a reaction called salt gel method, or you can do impregnation, and you can do doping, many kind of reactions. The principle is just converting the soluble salt into insoluble metal or metal oxide. If you want it metal, you have to control the environment. You shouldn't expose it to air. If you want metal oxide, you can expose it to air. There is no problem. And sometimes we need to calcine it or heat it at high temperature, because sometimes the surface of the material is hydroxide, and I want it oxide, so I have to heat it to remove the water. Okay? And the bottom-up approach is actually usually get you mono-displaced material. But usually, if you don't stop this process called the nucleation and growth. So you start with the nucleus, very small particles, and then it will start to grow. You have to control the kinetics of this process. You have to make it actually to start all the nucleation process at the same time, and then to stop, and then start the growth. If the nucleation, some particles start nucleation from early stage, and then another particle start nucleation at a later stage, this will give you poly-displaced particles. You have to control the kinetics. For example, 5 seconds the nucleation, from after 5 seconds the growth can start. And we use many reagents to control the size. Either templating agent we call it, or we can call it structure directing agent to control the size. If I want the elongation to be like needle or wire, I have to use certain chemicals to force the growth to be in this direction rather than going in the 3 dimension, for example. So you have to do some control in order to get the desired shape. Okay, how to characterize it? There is actually hundreds of techniques to characterize the nanomaterial, but the most important thing actually is the microscopy, because this will let me see the particles that I prepare. As I said from the beginning, we cannot see the nanoparticles by our naked eye or by the optical microscope, but I can see it by the electron microscope. So this is actually the 3 techniques that I can see: the morphology, the topography, the crystal structure, and the crystal size. But then there is many other techniques I will not talk about. This one, for example, to know how big the surface area. This is to study the thermogravimetry property. This is to study the crystal size, and most of them related to physics. I know XRD is actually XRD in geology, I think. Is it not belong to the physics, or
Yes,
XRD
X-ray
geology? Yeah, but I mean, we use it a lot in our sample. The main advantage of the electron microscope is actually we are replacing the light beam by electron beam, and the electron beam can decrease the wavelength to very, very small nanometer. Because we cannot see the nanoparticles in the optical microscope because the wavelength is too big. The wavelength of light, 400, is too big compared with my particles. So it will not scatter by or reflected by my particles. So I have to find another beam that will scatter by my sample. So we replace it by electron, which is very small, and you can control the size of the beam by changing the energy of this electron very simply in the device. One of the main disadvantages, you need vacuum because electron can easily interact with other electron even in the gaseous state, even with nitrogen or air. If the electron touch the air, it will also interact with it and get scattered. So we have to make ultra high vacuum in the microscope, electron microscope. But for light, atmospheric pressure is fine. There is lenses also, but here is glass, here is electromagnetic. The resolution can go up to 0.2 nanometer or even smaller than that. There's some now devices that can go to 0.1, and last time there was a seminar in the electron microscope unit. Somebody, one of the companies, they said we can reach the pico resolution. So very, very, very small resolution. The magnification can go to a million times here, and the focusing, of course, this is mechanical and this is electronic. So when you have your nanomaterial in the middle, there is, if you hit it with the electron, there is some signal bounce back from the sample, and there's some signal go through actually the sample, if my sample is very thin. This backscattered electron and the secondary electron, this is very important for the scanning electron microscope. This is one of the techniques. There is two famous branches of electron microscopy: transmission electron microscope and scanning. The scanning electron microscope is looking for this peak, for this electron and this electron. In the scanning electron microscope, there is two detectors. One can collect only the backscatter, and one can collect the secondary and the backscatter. But the secondary is much more. So the picture will be coming from the secondary, actually, not from the backscatter. This is very good for the morphology and topography. And this one is very good for the contrast. If you have material and you want to know the thickness, for example, if you have a metal and you want to know the thickness of the gold plating, because underneath the gold plating is a cover, for example. You want to know the thickness, this is the best technique to do it, because the gold is heavy metal, while the cover is a lighter metal. The heavy metal in the microscopy will look brighter, and the light metal will look darker because there is less electron coming from inside. So this is good for contrast, while this one is good for the shape and for the morphology of the particles. If you have very thin sample, there is some signal will escape from these samples and result in something we call it an elastic scattering of electron. This is actually related to the transmission electron microscope. Much higher resolution than SCM, much better because the column is actually have much different lenses and has aperture. We call it objective apertures. So you can control the resolution and enhance it much better. And you can increase the electron energy. You can increase it to 200 or 300 kV. While for electron microscopy, we can only have up to 50 kV or 80 kV maximum. And there is a signal here very interesting from the sample. Some of the electron, when you bombard your sample with electron, you are making, and when you eject electron, there will be, let's say, a hole in this place. Another electron start to coming down from excited state to the lower state. And because the electron comes down to the lower state, it will emit X-ray. It will emit light, but the light is actually in the X-ray range. And they found out each element will emit different X-rays, so I can actually know what element is this. If I have carbon, I will know how much carbon I have in my sample. This technology called EDS or EDX stands for electron dispersion spectroscopy or X-ray. Okay, very interesting to know the composition of the surface and near surface. The microscopy will not tell you only the surface because the electron beam is too high in energy that can penetrate to up to maybe 50 nanometer or more. This electron can go to 200 nanometer, while the secondary can escape from only 50 nanometer. So actually we are talking about the surface and near surface area. If I want to know the composition of surface and near surface area, the ADS is the best technique for that. If you want to know the composition of the whole material, you go to atomic absorption or XRF or other techniques. How much you have? I try to go faster.
Well, the thing is, usually...
I think half an hour.
Until 1:30.
Okay, I'll take 10 minutes maybe.
Yeah, if you finish earlier, that's fine.
Yeah. Okay, so this is the image of scanning electron microscope that we have in our college here. You can see, for example, this is what I call the EDS, the elemental analysis using SCM. You can see, for example, you can color this material with different color, and you know this is different material. Here I have two different material, maybe let's say copper and iron, and here I have, for example, chrome, and here I have chrome, for example, or gold and gold. Very clearly you can see it from the X-ray. It's like a fingerprint. Each X-ray will be responsible for a certain element, but you cannot study very light element like hydrogen or beryllium or boron. I think it starts from carbon nanotech. Okay, so and you can actually, for example, this is a plot of a substance. If you want to see all the elements, you will get something like this. You can hide one element and see the other element to know whether the distribution is homogeneous or not. For some material, the homogeneity of material is very important. You have, for example, alloys. You know, the alloys is two different metals mixed homogeneously in one place. If it is homogeneously distributed, that means good quality product. If it is not, that means you have a problem. I remember one time the Ministry of Health gave us a needle, and they want to make a tender actually to buy a huge number of needles, and they wanted to make sure this is good quality. They gave us two needles, and we tested by the ADS, and we told them very clearly this is better than this one. The material here is homogeneous, while the material in the other one is not homogeneous. And the same happened for the gold medal. The Minister of Education, they want to know how thick the gold, because the cost is actually coming from the gold, not from the chrome or copper. And the thicker the gold, the more time it will take to get corroded. If it is very thin, any scratch will make it exposed to the air. So they bring it for us, and we cut it in a small to study it from the side, and then we tell them this is thickness here, for example, a few micron, while there it's only 100 nanometer, for example. Okay, so this is called the ADX or ADS. This is a picture of iron oxide arranged in a shape very close to the rice shape, actually. You can see from microscopy, scanning electron microscopy, you can see the morphology very clearly, the shape of the particles. This is the image of the device that you have TM. For the high resolution TM, you can go to higher resolution that you can even see the small pores, because the resolution is set to can reach 0.1 nanometer or 0.2 nanometer, so you can see even very small pores. You want to know your material highly porous or not, and what is the size of the porosity, you can do it with this device. This is another example of cerium zirconium oxide material. You can see how crystalline it is. This is this is amorphous material, and this is crystalline material. But you can see very clearly, and you can know the structure of the material by doing the diffraction better. This is topography, some example. Okay, this is the nanoparticles that I told you. If you use the bottom-up approach with some sort of control, you can control the size of the nanoparticle. This material I prepared a long time ago, and we found out the particles is it's less than 5 nanometer. And you can see how homogeneous it is actually, how monodispersed it is. The particles are very, very similar in size, and we can disperse it very easily in a solution. So if I have application that will get benefit from iron oxide in a solution, this will be very excellent example for it. This is another material that I did with cerium oxide, nanoparticles. Now there is another technique called AFM. This is also very excellent for nanotechnology. The main advantage of this device is that we don't need the vacuum anymore. No need for the vacuum, because I'm not going to bombard my sample with electron. I'm going only to use a cantilever with a tip, very sharp tip, and then I'm putting X-ray, a laser on top of the cantilever, and the cantilever is made from material excellent in reflecting the laser. Usually, I think it's from silicon carbide or silicon nitride material, which is excellent for reflecting the sample. And then I scan my sample with the tip. Because of the topography, and there is a spring holding the cantilever from one side, it will shift down and up, and by this shift, it will scatter or reflect the laser with different angle. And from that, we can study the topography. You'll get a plot something like this. And you know how rough the surface is. We think that, for example, the surface is very smooth. For example, human hair, we think it's very smooth. But if you put it under AFM microscope, you can see it like the Himalaya mountains going down and going down. These details, you cannot see it by just normal microscope. This is the tip. This is the cantilever that I told you, and this is the sharp tip. And you can change the tip. You can make it sharper if you have very small particles. You can make it wider if you have larger particles. And you can do actually with this technique. Unfortunately, we don't have this in Kuwait University, but you can do it. You can study the magnetic properties and the interaction between the surfaces. So if I have material and I want to know what is the interaction of this material or this material, I cut my tip with the material that I want, and then I just bring it close to the surface to start feeling the attraction or repulsion. But I don't allow it to touch the surface. And from the attraction and repulsion, I can figure out what is the van der Waal, what is the interactions between these two material, whether they like each other or they hate each other. So it's very, you can do the magnetic properties also by the same method. This is how the laser, you just bombard the sample with the laser, and because of the topography of the sample, this will give you different angle for the lasers, and this will be converted to an image. Okay, I want just to talk a little bit about my work. Just go to just 5 minutes related to my research. I did a work related to catalysis, and at that time, this is a long time ago, I was aiming to decrease the contamination that we are sending to the air because of burning the natural gas. When you burn natural gas, the temperature reaches 1,400 degrees, about. So at this temperature, even the very stable molecule, nitrogen, can react with oxygen. Nitrogen is very, very stable. It cannot react at maybe 900 degrees or 800. But when you reach 1,400, the nitrogen reacts with oxygen, and we get gases called NOxes. This is very harmful to the environment. Actually, this is the reason for the acidic rains. And they consider it much worse in terms of the harming to the environment, much worse than carbon monoxide. Carbon monoxide that we get it from the coal, the NOxes is much worse than. So I was trying to use nanoparticles, nanocatalysts, that will drop the catalyst, the burning of natural gas from 1,400 to 1,200 or 1,100. This will do huge difference. If you just drop it by 100 degrees, huge difference will be. You will drop the NOxes by a large amount. So I did a lot of work, and I will show you quickly. This is how I prepared the nanocatalyst. This is the example. We tested first for the carbon monoxide, because if the catalyst is good for carbon monoxide conversion, it will be good for the NOxes. And we prepared pure cerium oxide and doped cerium oxide, different metal here, and here I use copper. And copper actually shifts the carbon monoxide total oxidation from temperature around 300 to temperature less than 100. So we can convert the carbon monoxide to carbon dioxide at very low temperature just by doping the cerium oxide by a small amount of copper oxide. So we shifted huge distance, and this work was published in several journals. And actually, this work, when I published it, the company sent me an email and they said, we want to talk about this work, and maybe we will link you with another company. But unfortunately, I think these people, they are trying to steal your idea. They are telling you, give us 2 pages more information about your product, and if we found it interesting, we will link you with the company. and they take the idea and they don't contact you anymore. So this happened to my friend recently. I told him, be careful, don't give them any information. The other work, this is the recent work, I work with a colleague from abroad, actually from MIT. This work is sponsored by KFAS. We want to enhance the recipe of the concrete. In Kuwait, we are close to the beach, first of all. We have humid weather and we have high temperature weather in the summer and low temperature in the winter, very low temperature in the winter. And this kind of condition is very harmful to the concrete and cement. So what we did, we prepared nanoparticles. One of my PhD students prepared nanosilica. Nanosilica is the silica is one of the main, let's say, composition of the cement. But if you add nanosilica, usually most of the research they are using large nanosilica, not nanosilica, they call it silica fume, large particles of silica. In this work we prepare around 60 nanometer nanoparticles, and we mix it with the cement, and we just cast it, and then we study its property, the mechanical property. I'll show you just one quick result. This is the reduced modulus. We did this in College of Engineering here. We have nano-indentation. This is one of the very important technique for studying the mechanical properties for the nanomaterial. But it has to be very smooth surface. So we took our sample and we polish it very carefully to make it very smooth, and then we study its mechanical property. And there is a physical property called reduced modulus. And we found out when we add 2%, when we add 0.5% of nanosilica, we get reduced modulus the highest here. And when we add nanosilica with metakaolin, metakaolin is a clay, one type of clay, we get also very high modulus. So we found out there is a, let's say, optimum value for nanosilica, and then if you increase it more, you are deteriorating the property of cement. And the same apply for the metakaolin, one type of the clay that we get from China. Now I have a project related to purification of water. We try to prepare high surface area material, which is actually, you all know this called charcoal or activated carbon. But we try to prepare it from natural sources like the chitosan, which is one of the main material from the shell of the shrimp, or from plant. We have a lot of palm in Kuwait or in the region, and also we have some other plant in neighboring countries. So we take this kind of material and we try to convert it to activated charcoal. This is very basic things that there's many research has been done in this field. But in my work, I try to increase the percent of nitrogen in the charcoal. This is very, very important. The highest nitrogen content so far you can get in charcoal is 9% or around 10%. If you can enhance it to 15% or 20%, this will make a huge difference in terms of water purification. So my main research is controlling enriching of the charcoal by nitrogen with different chemical method. Of course, after we prepare it from natural bio waste, and then we try to enrich it with nitrogen, and then we test it for water purification from heavy metal, for example, because the nitrogen has a lone pair that will catch the impurities, especially the heavy metals. This is a way we prepare some of the nanoparticles using film. I prepare film with my nanoparticle inside it, and then I burn the film. The film is actually from polymer, so you can burn it. When you burn it, you'll end up with the nanoparticles with very strange morphology that actually catch the attention of one of the journal, and they select as front cover for their journal. Journal Surgery, I submitted the work, and the alumina, it's very hard to get a face called iota. You can get it in terms of another faces, but the iota is very difficult. We get it by this film casting method, and they print it as front cover. This is another work that was selected for front cover. This is using the titanium with gold. You remember I told you titanium and I put gold nanoparticle. This will delay the recombination between the electron and hole. This was also published in PCCP, which is very good journal from the Royal Society of Chemistry. This is hydrogen splitting work I did some long time ago. This is converting CO2 to CO And actually, you might think this is actually not good for the environment, but CO have very interesting, let's say it's very good. You can convert the CO to methanol after that, and methanol is a biofuel. So instead of just releasing the CO2 from our factory, we take it to CO, we convert it to carbon monoxide, and then we convert it to methanol that we can use as fuel. So it's actually recycling the CO2. I did this work, we published it. I don't know if you attended the first nanotechnology conference in Kuwait. This was a long time ago, 3 years ago. I was the chair of this conference and I felt very proud to be involved. The last things I want to tell you, I proposed recently, in October, not very recent, a course related to nanotechnology for the university as a general course, elective course actually, but I want only to target the people with scientific background, like physicists, biologists, maybe engineers, and so far, still in the department. It takes us 1 year to study it in the department, which this is one of the bureaucracy that we have, but I hope I will manage to take it to the next stage to go for the higher administration and get approved. It will talk only about the basics of the course. We have very nice textbook for that. And the requirement is only chemistry 101 and physics 101, or chemistry 1110 and physics 121. So anyone study these courses, he can take this one as elective course. Okay? Thank you very much for